Hello students, we are looking at infinite geometric series. So here's an example for us. Remember, I believe in one of the first videos I talked about if you go into a store and you ask for one soda, and then the person behind you asks for half of a soda, then the next person asks for a fourth of a soda, and on and on and on you go, and the person behind the counter finally says, I will give you 2 sodas, and you can figure out how to split it up. Well, this comes from the idea of an infinite geometric series. So remember, the word series means that we're going to add up a sequence of terms. Geometric means that it has a common ratio. And then infinite means that it's not going to stop. It keeps going forever and ever and ever. So in this one, we have 1 plus 1/2 plus 1/4 and so on and so forth. So if we want to add all of these up, notice how this is going to infinity. So in our geometric series formula before, we had some n value that we were looking for. Well, now in this case, our n value would be infinity. So that doesn't quite work with the formula that we've been given, right? So remember, for a geometric series, so usually for a finite, we would have S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. Now, n, in this case, would have to be a finite number. But what if it becomes infinity? Well, then things change a little bit. So as we go to infinity, we have to figure out, well, what does that look like now? So for this series, we could write it a couple different ways. We could say that we're looking for the sum as n starts at 1 and goes to infinity. And we can write this the way that we've written it before. So what's our common ratio? Well, we multiply here by 1/2, multiply here by 1/2, right? So 1/2 times 1/2 gives us 1/4. So we could write this as our initial term times 1/2 to the n minus 1. And then just as always, we want to plug in some numbers. So if I plug in 1 minus 1, we get 0. Anything to the 0 power is 1. 1 times 1 is 1. So if I plug 2 in, 2 minus 1 is 1. 1/2 to the 1 power is still 1/2, and we get 1/2 there. Another way people might write this is they'll say the sum, n equals 1 to infinity, of just 1 over 2 to the n minus 1. So these two are equivalent, right? So remember, with our exponent, we can distribute that to both. 1 to any power just stays as 1. So really it's just that 2 that's changing. Now, if we plug this in before, we would start with 1 times 1 minus 1/2 to infinity over 1 minus 1/2. Well, that doesn't quite work as we're going to infinity. But I want us to think about that a second. So S sub infinity. If we wrote this out over 1 minus r, which is 1/2. Now, think about 1/2 as it approaches infinity. Well, will the 1 change at all? No. But the 2, what happens to the 2 as it's raised to infinity? Well, that will become larger and larger and larger. So what we're thinking about right now is basically the idea of a limit. So as something is approaching infinity, where is it going? This is kind of like when we talked about maybe end behavior, or if we talked about asymptotes. Where is something approaching as it gets closer and closer to infinity? So as 1/2 gets raised to a number closer and closer to infinity, that really goes away, right? Or it becomes very small. So we end up with just 1 minus 0. So 1 times 1, we get on the top. So this part goes towards 0. So we get 1 over 1 minus 1/2, which is 1/2. And we multiply that by the reciprocal, and we get the 2 that the person on the other side of the counter wanted to give us in the first place. Now this is an introduction to the proof of the limit of it, but you'll look more at that in future classes. I want to prove it using our algebra, similar to our proof that we did before. So let's look at, just in general, the sum, okay? So we have our proof here. So if we say s sub infinity, remember that we would still start with our first terms, right? So we'd have, if we have our infinite series, I'm going to write this on the line above. If I say I have n equals 1 to infinity of a geometric series, so a times r to the n minus 1. All right, so I'll start and I will have a. We know our a is really usually a sub 1. I'm just going to use a for convenience. So a, and then r, and we'll always plug in 1 for our first one, right? So notice how our n starts at 1 here. So if we put 1 in there, 1 minus 1, we get 0. Plus our second term, which would be a, our initial term, r to the 1, if we plugged in 2. Our next term would be a r squared plus a r cubed. But this would keep going on and on forever, okay? Now, let's think if we multiply each of these by r, similar to our proof we did before. So we're going to do r times s sub infinity. So the first term would become a r to the 1, right? Plus a r to the 2, plus a r to the 3, plus a r to the 4, plus dot, dot, dot. And it would keep going. So similar to our proof of a finite geometric series, we're going to subtract these and see what we're left with. So when we subtract s sub infinity minus r s sub infinity, and then when we subtract the rest of these terms, we can cancel out the ar1, ar squared, ar cubed. We would have an ar to the 4th over here. And I know some of you are thinking, well, we'll get to infinity, but won't this infinity at the bottom go one more than this infinity? Well, because it's infinitely large, and we're not multiplying it by anything else besides the same ratio, or the common ratio, then really the infinite terms will all cancel out. So what we're left with is a r to the 0. So here, we'll apply some algebra. Let's factor out our s sub infinity of 1 minus r equals a. And what does r to the 0 equal? Well, r to the 0 is equal to 1, right? Anything to the 0 power is 1. So then we get s sub infinity equals a over 1 minus r. Now, if you want to write it in how we've been writing things, we can say that this is our initial term. So this a before was talking about the initial term, and this is meaning the same thing. But sometimes you might see people not writing a sub 1, they'll just write a for the first term, as you've seen in some of the practices. So this equation is what we get for our infinite geometric series. Now notice how in our question before, we ended up with 2. So let's try to plug it in our formula and see what we get. So using the question from above, if we have our a sub 1, which is 1, divided by 1 minus our ratio, which is a half, then we end up with 1 over a half, multiplied by the reciprocal, and we end up with 2 also. So that checks with what we got up here. So I'm just going to star it, that we looked at this in 2 different ways, and we saw that we got 2 for both of them. So in fact, the person on the other side of the counter who when the people walked in and asked for 1 soda and then half a soda and a fourth of a soda, they were correct by telling them that they just will give them 2 sodas and they can figure it out themselves. So we have an infinite series, or an infinite series that's geometric, but notice what we have for our ratio. Our ratio is 1/2. Now, what if our ratio was that you multiplied by 6 every time? Well, if we multiplied by 6, the numbers would continue to grow and grow and grow, right? So would we be able to find one number that our values are reaching, that our terms are reaching, if it was a whole number that we put in for r? No, because it would continue to grow. So this works only when the absolute value of r is less than 1. Okay, so it has to follow that condition. If it doesn't, then it continues on. So if it doesn't, you are not able to find the infinite sum of a geometric series. So let's try another example. So if we have, find s sub infinity of 5 plus 3 plus 9/5 plus 27 over 25 plus ... So 3 dots means that we're going to continue on, right? So here we have an infinite series, and we're going to figure out what is our common ratio. Well, how did we get from 5 to 3? Well, we'd have to divide by 5, right? So we multiply something over 5, and that something would have to be 3, right? So 5 times 3/5, the 5's cancel, and we get 3. If we multiply again by 3/5, 3 times 3 is 9, over 5, we get our next one, right? So that's what we're going to multiply each term by. So if we look at our s sub infinity for this one, then we need our first term, right? So our first term is 5 divided by 1 minus our ratio. So our ratio here, remember, was 3/5. So we'll simplify. We get 5 divided by 1 minus 3/5. You don't have to show this step. Some of you will. 5 over 5 minus 3 over 5. So we're just simplifying the bottom there. We get 2 over 5. We'll multiply by our reciprocal by 5 over 2. We end up with 5 times 5 is 25 over 2. You can leave it like that, or because we have an exact decimal, you might see it written like that also. So we get our infinite sum of 12.5, or 25 over 2. So as we keep going to infinity, we will reach this. And notice the only way we could do this sum, is because the ratio was less than 1. So if our ratio would have been 5 over 3, well, that's not less than 1. So we wouldn't have been able to find the sum. So you would say that it doesn't exist, or that we can't find it. So here is, here's an example of this, and then you can see the example from before. So using this proof in our formula to help you find the infinite sum of a geometric series. All right, until next time.